Swayam Prabha. Digital India. Educated India.
Okay. Now I give you a sense that we design very interesting PTO. We thought we address a very important problem, but later we realize this PTO is not controllable, right? So the reason is we design one part. When we design this part, we didn't consider other part, like wave capture device design control system, right? And therefore, we want to have the control core design, and basically is optimization and iteration with considering all the three elements: wave capture structure, PTO, and control system. Okay, so and why we need to consider them together, right? And if you learn electric circuit, right, you can model the system, including everything using electrical element. And then when you harvest energy, every system there's input impedance, output impedance. You need to match the impedance with this. So then you get maximum power output. You design the system only with, for example, PTO design, and you didn't consider the power takeoff electric component, and you can take the maximum power input. Maximum power input not necessarily be maximum power output. Okay, so anyway, and you need a certain level consideration for the overall system. So in this class, we are also going to teach control core design, and okay, so another very interesting thing I want to show you, for example, this figure, this gearbox I mentioned, right, with one-way clutch. And these two figures look like that, almost same, right? So you have another turbine, right? So actually, another difference, you have a third one-way clutch. In this system, you will build a system, this hybrid wave and current energy converter. How the hybrid system work? The buoy move up and down to drive one generator, and the turbine also drive the same generator. Okay, so this hybrid system, in that way, we can get energy from both sources, right? So this line, you should say, the red line shows a combined system, wave and current. And the black line shows the current drive only, and this one wave drive only, right? And one side we can increase our power output, on the other side we can decrease the peak to average power ratio, right? As I mentioned that you want to have 100 kilowatts device, you have peak to average ratio 15, you have design your system to survive 1.5 megawatts. Now you only need to design to survive 400 kilowatts. So increase the peak to average, decrease the peak to average ratio. So, and then we are working on a project. This is flexible for meter application. So it's more like that. So what is this system? You want to put in the backpack quickly, assemble them together, put it in the ocean, right? So we use inflatable, flexible buoy instead of rigid, right? And we also use machine learning to optimize the shape. Instead of using CID, SolidWorks, make the drawing, do the NCC simulation, in MATLAB go through simulation, right? We can use the machine learning process, use one software to quickly do the iteration process. So, and fifth sample project is aquaculture, right? Nowadays, more and more seafood from aquaculture, not from wild caught from the nature. Okay, so we did a survey for the aquaculture company, and they gave us feedback. Okay, two most important things they need. Okay, one is the fish net cleaning, right? Fish net cleaning. So far, they have to diver to do the cleaning work every month, right? Another is dead fish removal. If there's dead fish there, the big marine wildlife will come here, break up the net. So they also use a diver to do this work. So instead of using diver, what we propose to do is to use underwater robot to do the cleaning work, and we have wave energy converter to harvest energy, right? So that is one funded by U.S. Department of Agriculture we are working on. And we advise our student team, they design cable-driven PTO, right? And they also build the system. This test in the, so we build the system and test in the tank, small scale, and test in lake. And so another thing, very important thing is how to design, drive the research convergency. I said this field is really multidisciplinary. Mechanical engineering, ocean engineering, electrical engineering, all this, civil engineering, it involves everything, but it's not enough. So this is just engineering. We need to consider the environmental impact. Ocean is a shared asset, right? It's not just one organization. You put there fishery or water transportation, right? They need or the defense, they need to share their water land. So water. So we need to consider environment. We need to consider social impact, right? And we also need to consider the coastal community. And so a common mistake or not engineers are making is we design something. Okay, now we test in lab. We try to put it in the market, we push, we convince the end user, the community to use that, right? So sometimes we even try to give the community for free, right? And we design system we can install for you, right? We feel very proud of ourselves. Wow, we are a good guy. We developed something to help the community. But we didn't ask them, is that what they need or not? Is that what they want or not? Right? So instead of that, we want to work with the community together, with social scientists, with environment scientists, then design the system at the beginning with consider or with engage of the community, or we call the community-centered design, right? So I mentioned that I work in a pharmaceutical company for 4 years. Now I learned one thing that can take advantage of my background, okay, to drive the research convergency. And pharmaceutical is different from most of the engineering industry, right? And mostly we have technology company. What technology company? It's technology driven. You have creative idea, you fail a pattern. Okay, now you want to bring to the market, right? This is called technology driven. And the pharmaceutical company is different, right? India is very good in pharmaceutical side, as you know, right? So pharmaceutical company, when they develop some drug, right? So it's not your chemistry or you invent some compound and you patent the compound you want to make a drug. Pharmaceuticals say, okay, there's one disease. For example, COVID pandemic happened, right? There's one disease, right? And you try to find what's going on with the protein, right? So you find a target. This is a protein target. So, and you want to screen all kind of drug, all kind of compound to have interaction with specific protein, right? After that, if some compound is active, you do further clinical trial, this type of study optimization, right? So that is called market driven, right? Or need. you have need first, then you screen all kind of concept, right? Therefore, from this experience, what we propose to do is community-driven design. So we work with the community first to understand the need. So this is market need. With this need, we screen all kind of possible design, and after that we narrow down several ones. Then after we narrow down several ones, we test in our tank, right, this system. Then have one or two go to clinical trial. Our clinical trial is ocean, right? One or two you put in the ocean. So that is my background. I propose this concept to U.S. National Science Foundation, the next idea. Okay, so again, don't think I know nothing. You jump in this field, you bring your experience here, and you address the problem, right? In the company, I learned two things. One is how to design the hardware. Second thing is how to jump into new field, even I know nothing. And you say pharmaceutical company, I know nothing about pharmaceutical, right? I jump in that field, I get promotion in 3 years, I get several awards, right? But I don't have such kind of freedom to look into new ideas. This is why I left industry to be my own boss. So in that way, I can look into new ideas. Meanwhile, when I jump into the new field, I try to take advantage of my experience, right? Like a motion rectifier design, I take advantage of my knowledge in the car industry, right? And this I take advantage of my experience, my understanding in the pharmaceutical company, technology-driven, market-driven, right? So technology-driven, market pull or combination. Anyway, so in our group, we collaborate with a lot of different places. So wave energy side, and so we need global collaboration, right? In this, recently we have one project and funded by National Science Foundation, and we can send 8 students to 4 countries. This is Norway, right? This is Denmark, and this is UK, British. This is Ireland. And in the next 3 years, we send 8 students to these 4 countries. We pay them as a PhD student salary at Michigan, and this student can be other university, right? And including airline ticket, they stay in these 4 countries 3 months, then come back to US. Okay, so another good thing is the University of Michigan side. University of Michigan, they charge a lot of tuition fee, and for graduate school, for undergraduate study, out of state or international, there is 61,000 US dollars. So it's very expensive. Meanwhile, they have a lot of resources. For example, I'm teaching this semester marine dynamics class. Marine dynamics class, University of Michigan support all the students to Taiwan, and they pay their round trip ticket. I take them 1 month in Taiwan, right? The students enjoy the trip. They get learned offshore wind industry, the wheel, right? Wheel energy converter, whatever like that. So that's a good thing, right? So they don't need to pay anything out of the pocket. I take them 1 week, go to other place. They can have a field trip. They can have interaction with different industry, university, right? We visit main course 2 universities. We visit many companies. Okay, so this is international collaboration. Wave energy need open mind collaboration. So, and let me say it way. Okay, my research lab I called Marine Renewable Innovation and Education Lab. Okay, so education is very, very important, right? When I was a certain professor, I want to get many grants, right? When I was an associate professor, I want to publish many papers. And later, after I become full professor, I realized students are more important. So this is why I pay a lot of attention to education side. And in August, I organized NSF-funded education workshop. In this workshop, we discuss what's the engineering innovation in the marine energy field, right? What kind of society, environment, economic impact the marine energy will have, and what kind of things the industry need, right? So I mentioned professional skills, right? This is very important too, right? Then how to engage the community, how to develop a curriculum to educate the workforce, right? And I give you a sense what we focus. So, and the industry engagement is very important. And we cannot just say university side we have some idea like that. We need to know the industry need. For this reason, I created such kind of industry university cooperative research center, Go Blue, growing ocean energy technology and blue economy. And University of Michigan here is the headquarters. We also have Stevens, cross side of Manhattan, New York, in New Jersey side, and Texas side. In this center, we work on something, usually technology readiness level from 3 to 5, basically industry-driven research with specific application in mind, right? This usually we call the venue of death. University usually here, industry here. Many university research just published paper, then died, right? We want to bridge the gap. So, and here we look into the problem. We have, this just needs some faculty member. We have about 40 faculty member, core faculty member from 3 universities. We look into dynamics and modeling. We look into power converter and storage, power management, then how to work on the environment society side to power with blue economy. So overall, wave energy side is really multidisciplinary research, right? So currently, my work and in this field and really engage multidisciplinary and from so let me say that way. In my group, I have PhD students with bachelor degree in ocean engineering, bachelor degree in electrical engineering, bachelor degree in mechanical engineering, and material science. Okay, so really different background. I want to drive the research convergence, and some of the students, I also invite them to have people outside, professor outside college engineering to be the community member so that they can learn policy, community engagement, and professional skills. So, okay, I just gave you some sample project, you get a sense, and this course, what we learn. You get the sense what kind of thing we need. Vibration, right? Fluid, wave dynamics, mechanical design, PTO, and electronics control, experiment, right? That is what we are going to learn, right? In that you get a sense, this design side, fluid side, electric side, control side, and in addition to that, we are also going to learn very briefly ocean current and offshore wind. Okay, so this probably you guys already get this. I copy paste this many words. I skip that. You can read it later. Okay, so it didn't go next page. Okay, so we are going to understand the key concept of the wave energy converter, right? We are going to learn practical knowledge, right? And we are going to say how then wave energy will be able to integrate real world application and blue economy side. So this course schedule, okay. And this introduction, then we are going to review vibration energy harvesting. Then we talk about wave theory and hydrodynamics. We talk about wave structure interaction, we talk about wave energy converter modeling in frequency domain, modeling in time domain, and we are going to talk about the alternating water column, and maybe we can skip a little bit because the students' background. Okay, and so we are going to talk about power takeoff design, control goal design, numeric modeling, and if we have time, and we may talk about modern system, and we'll tank test, and wave current interaction. So we don't have textbook. There are some nice reference I listed here. One is Fanny's class textbook, Ocean Wave and Alternating System. Another is Professor Farkow's lecture notes, Modeling of Wave Energy Conversion. Okay, so okay, about grading, how to evaluate. So we are going to have some homework problem, and we are going to have two exam. We are going to have course project. And by the way, this one, since I arrived here last night, and I didn't get a chance to discuss with Professor Samet and Dr. Vijay, and this is subject to change. Okay, just let you know. And the reason is I realize it might be very hard to assign homework to so-called grade second year student and PhD student, right? So we are going to update that after discussion with Dr. Vijay and Professor Samet. Okay, so now I open the floor for questions. Let us say 7 minutes questions before I go to talk about the vibration side. So as I mentioned to you, my research lab we call the Marine Renewable Energy Innovation and Education Lab. So what University in Michigan is Ivy League, public Ivy in the United States. Right, it has been in top 3 public university, and beautiful place, especially in the fall season, September like that. Winter time, you get a chance to see snow, right? And in Madras, you never get a chance to see the snow. Okay, so and we have facility. The tank is first is 110 meters. Time 60.4 meters. The depth is 3 to 4 meters. You measure center, that is 4 meters, edge 3 meters. It was built by Professor Herbert Sedner in 1904, 120 years ago. That is the first scientific research tank in United States. Okay, and so in our lab, we also have thermometer system. We can use PTO test. So currently in my lab, we have 2 scientists, and including 1 scientist who is currently in India right now to visit his family. Okay, and we have 4 postdocs, and we have 10 PhD students, and 1 staff who is the managing director of the Go Blue Center. Okay. So in this year, we are lucky to have 11 new projects from National Science Foundation, from DOE. We have postdoc position open and PhD students. So we are looking to students who can work on the control core design. So with the background of design, control, hydrodynamics, ocean engineering, like that, right? And I also need some people to work on the power electronics side. So now let me open second lecture notes. Okay.